Hi everyone, and welcome to the p-value fallacy as a data scientist with big data. This is my very first video here, so I just briefly want to introduce myself. I received my master's in advanced analytics and have been working in the healthcare field as a data analyst, a manager, or data scientist for around 7 years now. I love teaching and want to start a channel that focuses on statistics, data science, analytics, visualization, and a life as a working professional. Please ask questions. Let me know feedback on this video so I can incorporate that feedback into future videos because I definitely want them to serve you and be as useful as they can be. But let's get into it. What is the p-value fallacy and what do I mean when I say that? This is really a two-part problem. Part one is the problem with classifying something as significant or not significant. And the second part is what this video will mainly focus on, which is how a large sample size can destroy the meaning of the p-value. And as a data scientist, you often have access to more data and a larger N, and therefore will need to be mindful of this when trying to determine the strength and the significance of your findings. There are three main takeaways I want you to get from this video. The first main takeaway to becoming a better data scientist is that you should never be using a p-value of 0.05. And if you come across research that has been published that uses this large of a p-value, immediately be skeptical of their findings. This is really only appropriate when you have a very small sample size, say 20 or 30. But as a data scientist, usually you have access to much more data than this, and 0.05 is never acceptable. The second takeaway, which we'll go into more detail later as to why, is that you should be adjusting your p-value based on your sample size. The more data you have, the more noise we're going to expect in the data. And the more noise in the data, the more likely you're going to receive extreme results in your sample. Therefore, the higher your sample size, the smaller your p-value should be. The last main takeaway is that there are other ways to communicate the strength and importance of your findings besides using a p-value cutoff. The movement away from just reporting p-value as significant or not significant has been going on for many, many years, and people a lot smarter than me have been discussing how we should be reporting significance. Some examples of this would be using the effect size, the confidence interval, something called a decision index, which we'll get into later, and then actually reporting the p-value without your own interpretation of it. So how big of a problem is this? It's huge. This is not a problem that's new. Many statisticians, data scientists, and analysts have been warning about this problem for quite some time. Back in 2015, a gentleman by the name of Brian Nosek led an effort to replicate 100 social psychology papers and found that only 36 of them could be replicated. This wasn't only due to p-value, but that was a fault in a lot of the research published. In 2018, the Social Sciences Replication Project did a replication of 21 studies and found they could only replicate 13 of those studies. And although 13 out of 21 is certainly better than 36%, these are published studies which people base their research on, make decisions on, and which are supposed to shape our understanding of the world around us. So even just 13 out of 21 is still pretty sad. Further, the American Statistical Association has criticized the use of p-values and issued a warning about drawing conclusions from just the p-value cutoff. Researchers are now urged to report the p-value and not draw conclusions such as significant and not significant based on just a cutoff. Furthermore, there are countless publications, research papers, and scientific studies that use a p-value of 0.05, even though they have a sample size much larger than 20. If you want to Google examples of this, you'll kind of understand of how big of a problem this actually is. I'm going to mainly focus on how sample size ruins the p-value interpretation and why we have to adjust our cutoff. But first, let's review hypothesis testing in general. A hypothesis test is a statistical test which tells us if what we observed is likely due only to random chance or a statistically significant finding. This is done by having a null hypothesis, which is generally that there is no difference between groups and no relationship between factors. And this can also be representative of our current understanding of the population. The alternative hypothesis is what you expect your data to show based on your observations. So for example, the null hypothesis here is that there is no difference between group A and group B, and our alternative hypothesis is that there is a difference between group A and group B. The p-value is the probability of obtaining the observed results, or something more extreme, given the null hypothesis of no difference is true. So what does this mean? Say we had a p-value of 0.00001. This means that if the null hypothesis is true, the probability of obtaining the observed results that we did is only 0.001%. This would be pretty rare, and depending on our sample size, we would therefore likely reject the null hypothesis, or we would report this tiny p-value and say there is strong evidence to support our results. The smaller the p-value, the less likely the observed results are due to random chance. You can compare this to your cutoff. And comparing this to a cutoff kind of implies saying something is significant versus not significant, which is something we want to move away from, but I included this in here because this is still very broadly done in research. But generally, the smaller the p-value, the less likely those observed results are due to random chance. And to help understand this concept, I love this example of innocent until proven guilty. So let's pretend you're on the jury and evidence is being presented. Our null hypothesis is innocent, and our alternative hypothesis would be not innocent, or the defendant is guilty. So let's say all of the evidence has been presented, we analyze the evidence, and we get a p-value of 0.75. This means that if the null hypothesis is true and the defendant is innocent, we would still have a 75% chance of seeing the evidence we did. So this would lead us to say, no, this defendant is likely innocent. The p-value is 0.75. It's really high that we would see this even if they are innocent, so we are not going to put this person in jail. But let's say, what if we did our analysis, we analyzed all of the evidence, and there's only a 10% chance, given the defendant is innocent, that we would have seen the evidence that we did. I'm going to say, we're probably still going to say this is not enough to put this person behind bars. This is not enough evidence to say this person is guilty. There's a 10% chance this person, that this evidence would exist if this person did not do it. So we're still going to say they're innocent. But now what if all the evidence was presented and we have a p-value of 0.00001? This means there's only a 0.001% chance, given the defendant is innocent, that this evidence would exist. So this is pretty small, unless this is a really unlucky person. We're probably going to say this defendant is not innocent. And this is enough evidence to reject that null hypothesis. So hopefully that kind of understands how the p-value, how the smaller it is, the more likely we are to reject that null hypothesis, and then also how you can kind of think of a p-value cutoff and how the larger that is, the less likely we are going to reject that null hypothesis. And lastly, this commonly uses the Gaussian or the z-distribution. If our sample size is smaller than 30, which it probably won't be, we would use the t-distribution, but the higher the sample size, the more the t-distribution resembles the z-distribution. And yeah, the larger the n gets, the more the t-distribution resembles the z-distribution, and generally the t-table only goes to a sample size of 30, and then after that you would use the z-table. Now that we did a review on hypothesis testing, let's look at the assumptions that are required. The first assumption is that we have a representative independent sample and that the samples are random. And your sample is representative of the population, and each observation has the same chance of being sampled. And for example, if I'm measuring height for students in a college, I wouldn't want my sample to only consist of basketball players. And I also wouldn't want my sample to just be basketball players and their best friend. This would likely give me a sample which is much taller than the average student. We want numerical or continuous data, and this is just data that can be measured and represented in numerical format. This cannot be color or things that are descriptive. The population is normally distributed, or we have a large sample size greater than 30, or the population standard deviation is known, or a large sample size is greater than 30. I said or, but it's really and. And I put both of these together because generally when you sample from any distribution, you'll always get a normally distributed sample. But to make statements about the population also has to be normally distributed. And we also want homogeneity of variance. And what this means is that the standard deviation and variance between our two groups are going to be similar or the same. And to test this, you can use the F-test or the Levene's test. So let's look at the formula now that we have reviewed the concept and the assumptions. All right, so there's several formulas you'll come across when you're doing the z-test or t-test. They're all structured the same. I'm going to use this one where we're doing an independent sample t-test and then compare sample means. In our formula, we have our x bar, which is our sample mean. We have delta, which is our hypothesized difference between samples. This is going to be 0 because our null hypothesis is that there is no difference. We have our standard deviation squared, which is our variance. And then we have n, which is our sample size. And the main thing I want you to notice in the formula is that what happens to the formula when n increases. Nothing else will change, but let's say the number of members or number of samples we have increases. The smaller the square root will be of the variance divided by larger n. So the larger n is, the smaller this part of the formula will be. And the smaller that part of the formula will be, the smaller the overall denominator, the larger t will be. And the larger t, the smaller the p-value. So nothing has to change as far as the mean or standard deviation, but if n increases, the z or the t value will increase as well, which equates to a smaller p-value. So let's look at an example of this and think about how we would interpret this data. I made this example up, so just know it's not based on real data. But let's say we have the price of houses purchased in 2022 for first-time home buyers in North Carolina and South Carolina. We want to know if there's a difference in the price of the home purchased between the two states. Our null hypothesis here would be that there is no difference in the purchase price of a home for first-time home buyers in 2022. Our alternative hypothesis is that there is a difference in the purchase price of a home for first-time homebuyers in 2022. And let's pretend this is what the data looks like. For North Carolina, we have an average price of a home being $175,000 compared to South Carolina with an average price of $174,000. The standard deviation is around the same for both, with North Carolina having a standard deviation of 72,000 and South Carolina having a standard deviation of 72,500, and the sample size for both is 100. For most people who've purchased a home, this difference in cost is really minimal. There is no difference. The standard deviation is almost the same. And so kind of just looking at this data, you would say, okay, there's not really a difference between these two states. But let's go ahead and look at what the distribution looks like and what a t-test would show. So first, let's look at the distribution. Here we have the distribution of both North Carolina and South Carolina of the price of the home for first-time home buyers. Our blue line is North Carolina with 175,000 average per home and a standard deviation of 72,000. And then we have South Carolina with the average of 174,000 and a standard deviation of 72,500. And even just looking at this, they're about the same. There really is no difference between these two. But let's see what a t-test would show. And first, let's look at the data, the code that we wrote to conduct this t-test. So first we import the packages, then we create the North Carolina and South Carolina numbers. We calculate the z-score, get our p-value, and then print the results. So with our sample size of 100, we get a p-value of 0.922, which is really high. And this would really tell us there is no evidence that there's a difference between the cost of a home for first-time home buyers between North and South Carolina. We would therefore not reject the null hypothesis, and we would say there is no difference. But what if we increase that sample size and say, well, we have access to more data. Now we have a sample size of 50,000. Now all of a sudden, even though the mean and the standard deviation have not changed, our distribution hasn't changed. The only thing that changed is that we have more data. We now get a p-value of 0.029. So is there a difference all of a sudden now because of the two states? In the two states because we have more data? If we used a p-value of only 0.05, we would say, yeah, we reject the null hypothesis. But does this make sense? It doesn't. Furthermore, what if we had a sample size of $250,000? Now look at how small that p-value is. There's still no difference though. We know there's no difference between these two. We know there's no difference between North Carolina and South Carolina. This is only due to the fact that we have access to more data. This would look very significant to a lot of people, but again, nothing has changed. And this could cause us to question whether we actually found something significant and whether there is evidence to reject the null hypothesis, even though we know there's not. This is why it's so important to adjust our p-value cutoff. A p-value of 0.05 would make a lot of things look significant when they really aren't. Also keep in mind that a lot of programming languages might not spit out that many digits. It might just say less than 0.0001, but we need that full p-value and we need to understand how small it actually is. And then another thing to keep in mind is that with this example, we kind of know what housing prices are and what they look like, what a difference would be. But say we didn't actually really know the meaning of the data. Let's say we were doing something like we had data on how many hairs a cat has, and we want to compare species of different cats. I have no idea how many hairs a cat should have or what would be a significant difference. So if I got results with this small p-value, I might say, there is a statistically significant difference between the species of cat when there really isn't. And so it's so important to have domain knowledge on the data that you're using, and then to also consider things like the confidence interval, the effect size, the decision index, and to use a different p-value cutoff that is equal to your sample size, or not equal to your sample size, but adjusted for your sample size. So let's look at what we can actually do. Like I mentioned before, this problem is not new. Adrian E. Raftery in 1995 published a paper which, among many other excellent points, includes a different p-value cutoff for different sample sizes. And he suggests using evidence versus classifying something as significant versus not significant. Looking at this table, we see that standard p-value cutoff of 0.05 even for a sample size of 30, would really only show positive evidence, not strong evidence, and certainly not very strong evidence. And once you get to a sample size of 50, this would only show weak evidence. And again, as a data scientist, you're going to be working with a lot of data, and we have to use tiny p-value cutoffs. Just because we have a small p-value, as seen in our last example, does not mean we have strong evidence against our null hypothesis. So here are some other things to consider to be significant or not significant. Always use the appropriate p-value cutoff. I know I've probably beat this point to death at this point, but use the appropriate p-value cutoff. Use tables such as what Raftery created, and when you have a significant sample size, this p-value cutoff should be tiny. Avoid classifying results as significant or not significant, and instead use the effect size and report p-values and their interpretation. Use wordage like weak, positive, strong, very strong as suggested in that paper, instead of just saying something is significant or not significant, and then include that p-value in how you report it. Using a decision index. So this is something that's described in the use of p-values as a size-dependent function to address practical differences when analyzing large data sets, which sounds super relevant and like they've done a ton of research on this topic. But they suggest using a decision index, which adjusts for varying sample sizes and determining how significant something is and how strong your evidence is. And lastly, it's really up to you to understand and translate the results. It's also important to use context to deliver your insights so they can drive the most action. Often people are going to trust you and rely on you to give them those insights, and they don't really care about how you got to your findings or what your p-value cutoff is. So it's up to all of us to interpret results responsibly and make sure that findings are truly significant and not the result of a poor understanding of statistics. So I hope this video helped to drive the point home that we should all be careful using statistical testing with large sample sizes and to do our due diligence to make our findings have strong evidence to support them. Again, don't use a p-value of 0.05, adjust that p-value cutoff, and then use additional evidence to drive home whether something is significant or not, or report the strength of significance. Please let me know if there's any feedback, positive or negative. I definitely love to hear your thoughts and if this has been at all helpful. If any of the topics I discussed during this video are interesting to you, please let me know and I can make a video about those topics as well. Thank you, and please like this video and leave feedback.